To wrap up our discussion of black holes, we have a couple of more topics here. One of them is virtual particles. Stephen Hawking, mathematical physicist, theoretical physicist, introduced the idea of virtual particles, and this changed our understanding of black holes. Now, virtual particles come about because of his application of something called the Heisenberg uncertainty principle. In subatomic physics, quantum physics, there's something called the Heisenberg principle, and that is there are certain concepts or certain measurements that you can never make to 100% precision. They're always related to, you can only measure them to within a certain level of uncertainty. For example, position and velocity. You can measure where something is, you can measure how fast it's going, but in order to measure where it is, you have to be able to fix a particular moment in time. It's going to be a certain spot at a certain time. But velocity is change in position over time, which means it has to be in a slightly different spot. And the time it takes to go from one place to the other place gives you the velocity. Well, that means you can't really say it's at this velocity at this time, because velocity is over a range of time, and over a range of position. So you cannot measure exactly where and how fast with infinite precision. There's a slight bit of uncertainty. Now, the uncertainty isn't very much. The multiple of the uncertainty and the in position and the uncertainty in velocity are related to something called Planck's constant. And Planck's constant is, like 10 to the minus 34. It's a tiny number. And so this is not very much uncertainty, but it actually is an uncertainty. And at the subatomic level, that uncertainty really matters. So you can't, for example, with all certainty, know exactly where an electron is around an atom. And that's an application of this Heisenberg uncertainty. You also can measure with infinite precision energy and time. You can measure energy, but not exactly when it's that energy. Again, this is a level of uncertainty. Now, this is where an interesting thing comes in, because Hawking says, if you have a particle and an antiparticle, if they come together, they annihilate each other, and you have energy equals mc squared. But if you have that energy, you can actually make a particle and an antiparticle. So what he says is, you can have this energy to make a particle-antiparticle pair. So a proton and an antiproton, or a positron and an electron. And so you have enough energy to make them. And if they almost instantly come together, they annihilate each other and release that energy. But the energy and time are uncertain. So that means that this delta T in physics can be plus or minus. And Hawking was the one who realized it could be plus or minus. So the energy could actually be released a fraction of a second later after they annihilate, or a fraction of a second before they annihilate. But if it's before, that might have been the energy that made them in the first place. So in other words, you have this energy, and you just suddenly get this energy. You make a particle-antiparticle, which almost instantly annihilate each other. And when they annihilate each other, the energy goes backwards in time and makes the particle in the first place. And so there's nothing there. Suddenly you have this tiny bit of energy that comes from a fraction of a second in the future to make the particle-antiparticle, which in a fraction of a second later, they're gone because the energy went back into the past and made them. And so there's only something there for this tiniest fraction of a second. And so they're like practically not even there. So they're referred to as virtual particles. Experimentally, we've actually verified that virtual particles exist. And so this idea was this huge step forward in understanding what's happening at the subatomic level, but in terms of black holes, it was an interesting application. Because he realized that a particle-antiparticle pair could form right near the event horizon, just barely outside the black hole, and one of the particles could actually fall into the black hole, and the companion might escape. Well, now the energy doesn't go backwards in time. to make the particle. So the energy has to come from somewhere. So the energy equals mc squared comes from the mass of the black hole. The black hole actually ends up losing mass by a tiny little bit to make this particle that went shooting away that did not get annihilated by its virtual antiparticle. And so that means that near the surface of a black hole, there's these particles that are constantly streaming away from it, particles and antiparticles. And so we call that Hawking radiation. And so as these things go streaming away, then the black hole gradually loses mass. And so we'd say it evaporates. Okay, now by evaporating, don't think it's very fast. Because small black holes can evaporate very quickly. But a black hole like the size of Cygnus X1, this mass of the sun, would take 10 to the 67 years to evaporate. What's 10 to the 67? There's not even a name for a number that big. That 10 to the 67 is a bigger number than the number of seconds in the age of the universe. That is a number bigger than the number of protons, neutrons, and electrons in the galaxy. It's a number bigger probably than the protons, neutrons, and electrons in the universe. So that number is enormous. That's how many years it would take for Cygnus X1 to evaporate. Even a black hole the size of the Earth's mass would take billions of years to evaporate. A black hole of only 250 metric tons would take about a second to evaporate. Well, the smaller you get, the less time it takes to evaporate. So a black hole that's much smaller would be even less. In fact, a black hole the size of a subatomic particle would evaporate in virtually instantaneously. And so tiny black holes would instantly evaporate. Big ones would last for a very long time. When the Large Hadron Collider first was turned on in Europe, there was actually speculation that it might make these microscopic black holes the size of subatomic particles. And of course, once someone said that, it was like, oh, that's kind of interesting. At least physicists thought, hey, that's kind of interesting. The non-physics people went into absolute panic mode, thinking it's going to destroy the universe. And the physicists were going, oh, no. I mean, such a black hole would evaporate before it even got to eat anything. Even if it ate anything, it'd eat like a proton or something, and then evaporate instantly. And so there'd be no chance to destroy the world. But anyway, these little tiny black holes should evaporate very, very rapidly, and this actually raises some interesting questions, which are beyond the level of the class. But so that's black hole evaporation. It has to do with these little tiny virtual particles. Again, black hole the size of a proton would last 10 to the minus 100 seconds, and again, there's not even a name for a period of time that short. In fact, a period of time that short is mathematically essentially instantaneous, because that is too short of a time for even the physical laws of the universe to apply. Okay, so the next question is, what would have you fly into a black hole? Why would you want to fly into a black hole? Well, that gives rise to our very next topic, which is something we call wormholes. So, what's a wormhole? Remember a rotating black hole? You have that circular singularity in there. Well, mathematically, that circular singularity, the space inside, is pretty much the same as the space inside every other circular singularity. So if you fall into a rotating black hole, and instead of hitting the singularity, you pass the hole in it, then you're not, because they're all the same, you could essentially you have a choice as to which black hole you're in. So you could fall into one black hole and be inside of another black hole. And so you fall into one black hole, and and you can be like inside another black hole that's in a different galaxy even. So you can fall into a black hole in the Milky Way galaxy, and then as you pass through that circular singularity, you're in a black hole in the Andromeda galaxy. Well, the thing is, you're still in a black hole, and so you're still stuck in a black hole. Now, in the early days of talking about wormholes, they talked about the possibility you fall into one black hole and you come out in like another universe, or you come out somewhere else in the universe in like a white hole, like which is an anti-black hole. But mathematically, while the idea of a white hole looks interesting, we've never seen any evidence of such a thing, or how you'd make such a thing, or anything of that sort. So chances are, you fall into a black hole, you're stuck in a black hole. Remember, you can't get out of a black hole. Okay. So these things are called wormholes. At least that's the layman's term for it. Is connection between one black hole in one part of the universe and a black hole in another part of the universe. Einstein-Rosen bridges is the physics term for it. And theoretically, they should have been formed when the universe formed, but they're tiny little things, something less than the size of the nucleus of an atom. So it would allow like a quark or a gluon to tunnel or to like transfer itself from one side of the atom to the other without really having to go through the space in between. But that's about as far as you can go with it. It's not going to go from galaxy to galaxy. That doesn't stop science fiction, however, from having tons of really cool stories about wormholes that link one part of the galaxy to another part of the galaxy, or one galaxy to another galaxy. And so it's a staple of certain kinds of science fiction. It's really cool. As a sci-fi nerd myself, I really like the idea. But the reality is that you're still stuck in a black hole. And so that does kind of take some of the coolness out of wormholes.